right, let's start. For those who are coming in, there are some seats all the way up the front, down here. Feel free to take them. So I've worked a while ago at a company where the director of the company once said, if a good technical design has been made, then writing the code can be done by a programmer with the IQ of a monkey. Who agrees with this? I see we have a couple of architects in here. But you better not raise your hand too much, because there are loads of developers in here who are going to go bananas if you raise your hand, right? But what if I rephrase that statement to, if a good technical design has been written with instructions on what to change where in the code base, the code can be written by an AI. Who thinks this could be true at any point in the near future? Okay, that's a bit more. So I guess, well, we collectively agreed that the current state of AI outperforms monkeys in writing code. That's a useless fact that we cannot do anything with. But all jokes aside, I think we can probably agree that design is a significant part of software development. So let's talk about making design decisions. My name is Bert Jan Schrijver. I'm CTO at Open Value. I like to explain CTO as Chief Troublemaker Officer, which somewhat is true every now and then. I'm also in the board of the NLJUG, the Netherlands Java User Group. Any NLJUG members in here? Yes, my people. So the next 45 minutes or so, we're going to look at a couple of definitions to start off on the same page. I'll tell a story about flexibility in software. We'll look at levels where you can apply design choices in choosing for generic or specific solutions. I'll give you some tools to help decide if you need to make design decisions yourself. We'll talk about the cost of generic solutions, when and why it makes sense to go generic. We may have time for a bonus topic about sharing code inside an organization, and we'll end with an end. But let's start with a question. How many of you are in some way involved with software development? Yes, everyone, right? That's obvious. So ask yourself, what is software design? How would you describe software design to a colleague or a friend? I'm not wanting an answer for you, just to give it some thought. So, well, if you look it up on Wikipedia, it says that it's the activity following requirement specification and before programming. Or software design usually involves problem solving and planning a solution, or the process of envisioning and defining software solutions to one or more sets of problems. Well, that's Wikipedia. I think that's decent, but it's 2024. So I also asked ChatGPT. And ChatGPT says it's the process of defining the architecture, components, interfaces, and data for a software system to satisfy requirements. It involves making decisions about how software will function, how parts will interact, how it will be structured in order to solve a problem or to achieve a goal. So the design is basically coming up with solutions for problems, right? So then often I get questions like, when is something design and when is something architecture? So a question I often ask in return is, does it really matter? They're both acts of designing a system, albeit maybe in different levels. Both are about making significant decisions, where significant is measured by the cost of change. If you make a decision that turns out to be hard to change, that's a significant decision. If I would need to make a distinction between design and architecture, I would say that design is typically local. So something within a class, within a project. Architecture typically on a bit higher abstraction level, on a project level, organization level. And my point is that you can make choices between generic and specific solutions on different levels in your system, in your organization. And the same discussion often plays with the requirements. So we have a requirement. Is this a functional requirement or a technical requirement or non-functional and quality requirement? Well, does it matter? They're all requirements, right? They're all capabilities that the system needs to perform or requirements that the system needs to conform to. So in the end, again, it's about making significant decisions that shape a system. So now we somewhat know what design is. Let's ask ourselves, what is a specific solution in a design and what is a generic solution? So a specific solution is something you make for a single place, for a single occurrence. It solves a single problem, a specific scenario. A specific solution may not be easily adaptable to other solutions. Mind you, may not be, it may be. And as engineers, we love crafting intricate and smart solutions, right? We want to write code that shows how smart we are and how well this expresses our amazingness at programming. So I know a colleague that that was sat next to me and once said, "I recognize this code. This code is written by X. I won't name this person." And I said, "Why do you know?" "Oh, it looks amazing, super smart. It does all those things at the same time, but I have no idea how it works." So this is an example of a clever solution, right? So a generic solution is typically flexible and reusable. You can use it in multiple places. You can use it to a wide range of input problems or scenarios. It's something that you can use in more than just one place. So whenever I talk about generic solutions in this talk, I'm talking about shared code. So you abstract some piece of logic to some shared place, can be anything, and multiple places in your code base, in your project, in your organization, use this piece of shared code. And when we're talking about used in more than one place, it can be anywhere in a class, a component, a service, an application. So to talk a bit more about that hierarchy of solutions, I'd like to introduce a concept to you. And this is called hierarchical decomposition. So hierarchical decomposition is a way to basically break a system or a problem into smaller parts that are easier to understand. And to give an example, if we would look at Google search, for example, on the top level of abstraction, Google search performs search for you. So if you would draw an architecture diagram of Google search and you zoom in one level, you probably get like there's an indexer component, there's a search component, there's an ads component, there's a ranking component. And if you would then zoom in one level deeper, you go to the indexer, then there's probably an explorer that maps out the internet, a spider that scrapes HTML, a parser to parse that HTML, etc., etc. And on all those levels, you can make these choices on solving stuff in a generic or specific way. So this zooming in and out in different levels of abstraction and detail is, I think, a core concept of software architecture. It enables you to reason about systems at the right amount of detail and also at the right amount of abstraction. So abstraction also means leaving out necessary details to be able to explain a system at a higher level. So the C4 model by Simon Brown, I think, is a good example of this. Real short, it starts with the top level is the context of the system. So which other systems surround my system? You zoom in one level more, that's containers. Those have nothing to do with Docker containers, but this, for example, the container here is a web application. If you zoom into that, you get the components of this web application. And if you zoom in one level more, you get code. So being able to zoom in and out, I think, is a core concept of reasoning about systems. And let's talk about another concept of reasoning about systems. And this is coupling. So coupling, well, basically when you change something and something else that you don't want to change need to change as well, you have coupling. So you could explain as the interdependence between building blocks. So a building block is anything you use to build your software. It could be a class, a component, a module, a service. It's a generic term for a block you use to build your software. So coupling is a measure of how closely connected two components are, or better, two building blocks. Low coupling is often a sign of a well-structured system because it enables change. You can change stuff in one place without needing to change stuff in another place. And it's usually contrasted with cohesion. So cohesion is the degree to which elements of a building block belong together. So it measures the strength of the relationship between pieces of functionality inside a component. So in cohesive systems, functionality inside components is strongly related. And usually this contrasts with, if you have high cohesion, you also have low coupling. So there are loads of different ways in which you can have coupling in systems. So you can have coupling via inheritance. You inherit properties or methods from a superclass. Through messages or events. You're sending messages on a queue or an event bus or a Kafka topic to multiple subscribers. And you need to change one of these messages for one of the subscribers. Now the others may need to change as well. Temporal coupling is another way, where component A depends on component B in time. Component B needs to have done something for component A to before component A can do its work. You can have coupling via data types. Maybe you have some classes that represent the data type. And 3 services use this class to marshal POJO data between those services. If 2 of them want to change and the third needs to change as well, you have coupling through data types. The same with JPA entities, for example. Coupling via data is also possible where you depend on information in a database. You change something, something else needs to change as well because the database record has changed. And all other types of coupling via code or APIs, whether binary or source. You cannot make any non-trivial system without having some form of coupling. But be careful with coupling. So I was recently reading the book The Unicorn Project by Gene Kim. And in this book, Gene discusses the 5 ideals of DevOps. So the first ideal is locality and simplicity. So locality is a degree to which, if you want to change something, you can change it in one place, instead of needing to make many changes in many places. So locality requires simplicity. If you don't have locality, and you need to change stuff in lots of places, then there's dependencies, so you have coupling. And I'd say that dependencies are well, one of the mothers of all slowdowns. They prohibit you from moving freely. You can see them as handcuffs. And also realize that as soon as you introduce a generic solution with shared code, you are introducing coupling. Every generic solution introduces coupling. So if you copy-paste a piece of logic to another place, there's no coupling. If you move code to reusable component and now depend on that component from 2 places, there's coupling. Obviously, there's lots of different types of coupling, and there's lots of degrees in coupling. Usually we strive for low coupling, which means that things are easy to change. But every generic solution introduces some coupling, and this is one of the drawbacks I want to zoom in a bit more. So how many of you have heard or read about Clean Code, the book by Robert Martin? Yeah, that's 2/3 of you. So one of the principles that Uncle Bob explains in this book is dry, right? Who loves dry? Don't repeat yourself. Oh, that's not everyone who read the book. Interesting. So there is a risk with dry, because don't repeat yourself, which means as soon as you have code in one place that you need somewhere else, you should not repeat yourself and copy it, but you should extract it and share it. So strict adherence to dry also increases coupling in your system. So don't follow dry in a vacuum. So if you kill duplication in 2 places, then you're also taking responsibility for predicting that those 2 things will change together from now on in the future. So how do you know? And you're also likely to create confusion and extra work for little benefit. So a trick of knowing when applying dry makes sense is if you can find a really good name for the component that you're extracting. If you can, then it may be a good idea to make it generic. If not, maybe stay away from it. So we all know that it's bad to repeat yourself by duplicated code. But what if I tell you that duplicated code doesn't hurt until you need to change it? And that moment may never happen. So let that sink in for a little bit. Premature code, preventing code duplication can be a form of premature optimization. And you may not agree with me on that, and that's fine. We're not here to agree. And even if you need to change duplicated code, so code that's in 2 places, we have pretty good IDEs nowadays that can do regex search replace. There's tools like Open Rewrite that can automate like large-scale refactoring changes. So often we do things because we have in our minds that we need to be future-proof, right? What is future-proof? Should we be prepared for future changes? Sure, nobody wants a system that's unchangeable, right? But isn't saying that we want to be future-proof the same as asking, can we predict the future? Last time I checked, we weren't too good at that. But design should be structured to accommodate change. So you should think about future accommodations by making your system easy to change. So you can be prepared for any change in the future by making your system as simple as you can. But since we don't know what the future will bring, there's also no really such thing as future-proof. So what I like to do here is to apply risk management. So again, this is, design is about the cost of change, and when a decision is significant, then it may take more, significance is measured by the cost of change. So if you make a choice, it's a lot of work to change it, then you may need to think a little bit more about it. So whenever you need to face a decision, think about, if this turns out to be the wrong decision, how bad is this going to be? So let's say you need to make a decision whether you, I don't know, use library A or library B for a single API call you need to do. And you're pretty sure this is the only API call you need to do at any point in the future. If this turns out to be the wrong choice, then you can probably swap out that library for another one somewhere in the future. But if you make a choice that's fundamental in your application, something that touches all your classes in your code base, and it turns out to be a wrong choice, then it may be a lot of work to change this. So apply some risk management here and think, what if I get it wrong? If it's not a big problem to fix it later, then, well, let's move on. I have an example about this. So this is a story about flexibility in software. So I joined the company a while ago, and it was a super modern tech stack. So it was EJB 3.1, JBoss, I don't know, something, Groovy something, and JSF. It was super modern in, I don't know, 2011 or something, right? I set up my local environment, and I wanted to get started with working on this application. And when I loaded like the starting screen, the home screen of the application, it was quite slow. It took a couple of seconds to load like a simple home screen. So I asked to my colleague, by the way, the same colleague that made that code that was recognizable, but it was not his fault. Like, why is it taking so long to load this home screen? He said, yeah, there's probably some queries being executed. So I said, okay, how does this work? Yeah, that's with Hibernate, and we automate those queries. And I said, okay, I know a couple of things about query optimization. So can you show me the query? He said, yeah, sure, I will print the query for you. So I said, okay, fine, and I can have a look and take my pen and pencil to make some notes on what we may be able to optimize on the query. So he walks off into the hallway, and he comes back like 20 minutes later or so, with a stack of paper this big. I said, what did you do? Why are you gone for so long? He asked me to print the query. I said, but what did you bring? This is the query. It was like, I don't know, 6,000 lines of generated mess of code. The reason was that the data model was super complex in the system. And the reason for this was architects. I'm a software architect myself, so I like to make fun of people like me. But these were architects that were hired. This was a public tender, and the architects were hired by the local government to make a design for the system. And they were not technical, I don't know, like information architects or something like this. And their experience was that software systems were hard to change. They had designed systems before, and they found out that when they had made a mistake in their design and that needs to be changed, it was a lot of work. And they wanted to prevent the customer from this by making a system that was super flexible. So what they designed is a system where on every screen, via a management interface, you could add extra fields. And on every drop-down in the system, you could add extra fields in the drop-down. And then to make it worse, there were two systems that needed to synchronize together. Whenever somebody says synchronize, ask them, you mean sending data one way? And when they say, no, it's both ways, then either run away or ask them to change it. But the point was the data model was so complex because everything was customizable. As a result, the whole, let's say JPA model of mapping this super flexible model to the database became super complex as well. This project stopped at one point because we were unable to finish it because the data model was so complex. And in the end, we did get it live by throwing away everything and making a really simple system. So again, here you can be future-proof by making something that's easy to change, and not by making stuff flexible by adding configurable database fields on everything you do. So Stefan Tilkov, who unfortunately passed away last year, he said it best: highly specific code is often preferable to sophisticated configuration. And I think he was super right. So everything so far we've talked about builds up to this. Let's start. So if you need to make choices about generic or specific solutions, let's zoom in a bit on those levels where we can make those choices. So on a code or a class level, am I going to reuse a method here or not? If you want to use, well, if you generate code or write it manually, I don't mind so much on how generated code looks, as long as you generate it every time that you need to change it. If you go ahead and changing generated code, then it's your code, then it's human code. But if it's purely generated code, I don't really mind how it looks. Are you going to use a library or not? Are you going to build it yourself or extract logic to a generic library? That's also a way of genericizing stuff. Are you going to have a generic data model inside your team, your department, your organization, your country, the world? I used to work for a company that did a lot for insurers, and there was a standard. I'm not against standards, but they have their drawbacks. There was a standard for exchanging data, I think it's still there, exchanging data between insurance companies and intermediaries who sell insurances. The standard was called GIM. So GIM stands for Generieke Interface Manager, which roughly translates to Generic Interface Manager. There's two problems with this term. It is an interface, that right? But it says generic and it says manager, and both those things are scary, right? But the problem with GIM was that it was standardized, and there were like 10s, 20, 30s of companies in the Netherlands using the standard to exchange data. So every now and then we would do an implementation with the GIM standard, and then we found out that we had a piece of data that didn't fit in any of the standards. So we had a data catalog, and the data catalog described all the fields and their meaning, and then we had something that didn't fit. So then we called the CV, which is the Standardization Institute for Insurers, and we said, yeah, we have this piece of data we want to exchange, but we don't think it fits in the standard. And then, well, later they called back, yeah, we've looked at the data catalog, and indeed, this does not fit in the standard. Okay, so I'm glad we agree. So what do we do? We're going to add a new field to the standard. Great, so that I can put my stuff in there. So when can I use it? Well, the next release of the beta version of the standard is in 2 months, and then there's a 3-month grace period for everybody to give their feedback, and then we release it. Okay, so like 5, 6 months? No, then everyone has half a year to implement the new standard, so it's like in a year or something. So yeah, you end up calling the insurance company and say, can we misuse this field for putting the data in there so we can continue right away, right? On a service or microservice level, are you going to extract logic to a generic microservice and call this for multiple parts or not? And even on an organization level, when do you keep something specific for your project, but when are you going to reuse a service or a library in your whole organization? It may have speed benefits because it may be faster for you to do new things, but you also get coupling in return. And what I want you to take away from this talk is to be careful in weighing this trade-off. So everything in software design and software architecture is a trade-off. There's never a clear yes or no. The trade-off with generic versus specific is I have reusable stuff versus I get coupling in return. So how do you decide whether to solve something in a generic way or in a specific way? Well, a couple of tools to help you decide. The first one is you can ask yourself, do we really need this now? Yagni, you ain't gonna need it, or you ain't gonna need it yet. So an example for Yagni, and I'm curious how you think about this. You have one piece of logic that you need to talk to. So you're creating like a class with a public interface, and you may have future implementations of this interface as well. Are you going to create a Java interface right away, or are you going to talk to a concrete interface? Let's say you're going to make something in a database, and you may change your database implementation later. Are you now having your business logic going to talk to the concrete implementation, or you're going to extract an interface now and have everything talk to the interface? Who would always add an interface, even if there's only one implementation? Okay, yeah, that's fine. And who says I'll just go with the concrete implementation and may add an interface later? And that's more people. Okay, I'm happy to see that because I agree with the second group. I don't have anything against adding interfaces, but the point is you don't know yet if you have the right interface if there's only one implementation. So a second question you can ask, or actually 5 questions, is the 5 Ws. So I'm going to explain it slowly to you because the 5 W's are often misunderstood. The first W is why. Why do you want to do this? Why do you want to make this generic? The second one, this is the most difficult one, is why. So when somebody gives you an answer, you keep asking why till you get their answer. Then the third one is simple, that's why. So you ask again why, and you repeat this 5 times until you don't get any answers anymore or you really get to the why. So keep asking why you do this. Why are you adding an interface here? Yeah, because this database implementation may change later. Why do you think it will change later? Yeah, because maybe we will switch from Postgres to MySQL. Okay, why do you think we're going to switch? Yeah, because I don't know. Okay, if you don't know why you're adding an interface now. 5 W's, and the second is a W, which means why. Time and effort for generic first specific. So a generic solution may be more work, maybe less work. A specific solution is usually less work. But you should also look at mostly at how much work is it now. Because if you have a specific solution, it's always possible to change this into a generic solution later. If you make it generic now, you may be spending effort now that's not necessary, that you need to revert later. We'll look at this in a bit. And there's also the myth of the first time right. So there's the first time you see a problem. Usually you don't understand the problem domain enough to, so what's my actual problem, to fully understand the solution domain. Which solution options do I have? So often you don't get a solution right until you've built something 2 or 3 times. So this is also why you should wait a little bit before you make something generic. Think on complexity and scope. How complex is the problem? Is it really well defined or not? These may also have impacts on whether you solve something specific or not. If it's super clear, well defined, then you can make a specific solution. If it's something that's super complex, well, it may help to make a generic solution because it forces you to think a bit more. And having a generic solution may also encapsulate the complex logic. We'll talk about that in a bit as well. That sounds a bit counterintuitive, but I hope I can make it clear later. And then the rule of 3 that we'll look on at the next slide. So it's also important to consider any potential future needs and evolution. But well, how do you know? Reiterating to my previous point, right? So if you already know stuff is going to change, sure, then you can accommodate for this. If not, you can accommodate for change by making stuff simple. So my friend Gunnar Morling, who is also around here somewhere, I think he said it best, a fair share of software design is professional procrastination. So postponing making a decision, keeping options on the table for as long as you can to prevent putting yourself in a corner by committing into a direction or a solution that turns out to be a poor direction later on. So the rule of 3 is simple. When you're reusing code, the first time you copy it, and you don't start abstracting until the 3rd use case you have for this piece of code. And this helps you avoid writing the wrong abstraction, because you don't understand the problem fully. It's also easier to make a good abstraction from duplicated code than to refactor the wrong abstraction, because then you're forcibly trying to fit whatever you designed first into the 3rd use case. This is often also called 3 strikes and refactor. So the first case, you see a problem, just build it, don't genericize at all. Solve the problem in front of you. Think about you ain't gonna need it yet. Then the second case, you duplicate the original, maybe you redesign a little bit and you extract some common behavior while you change. And then when the 3rd case comes along, if it comes along, examine the lessons you've learned from the first 2 cases, and then design a generic solution that will make it easy to add your 3rd case. Then you see you're already benefiting from the generic solution when you're adding your 3rd case to your solution. So it's already saving you time, but it's also saving you time because you didn't go in the wrong direction too early. So another tool I like to use is strategic design. This is a concept from domain-driven design, and it's a tool to help decide if you solve something generic or specific. But more, it's about building something yourself as an organization, as a team, or not. So in strategic design, there's a couple of subdomains that are identified, and we're looking at it from the perspective of, let's say, custom software development. So we're writing actual code ourselves. So the first one is your core domain. And the core domain is what makes your organization special. Without the core domain, your organization cannot function. It should receive the highest priority and probably also the best teams to work on it, because this is the reason for existence for your company. This is why you're writing this custom software. A supporting subdomain is necessary for the organization to succeed, but it does not fall in the core domain. So it's not just special for your organization. So you may be able to start with something existing and tweak it to extend it to your specific needs. And then finally, a generic subdomain is something that does not contain anything special to your organization. It is still needed for the overall solution to work, but you can save a lot of time to use something off the shelf or a library or whatever. So for example, stuff like accounting, invoicing, identity management. These are usually things you don't need to build yourself, because you can get solutions on them on the market. And then there's another factor to consider, and this is Conway's law by Melvin Conway. And Conway said that organizations design systems that mirror their own communication structure. So what can you learn from this? Well, one thing is that you shouldn't force a solution that goes against the organization structure, because probably the organization is not going to want to use it, because they're not used to work in this way. And I guess the point, specifically within the context of generic or specific, is be careful to force generic solutions on an organization when teams don't want to work together. So if you have 3 teams that don't want to work together at all, and you give them a library, they need to develop together and evolve together, you're probably going to get fireworks, but not in the right way. So to give you an example in the impact on Conway's law on choosing a generic for a specific. So I worked at a company before who wanted to create, well, let's say a new range of systems. And there were 3 business units in there. And they all somewhat wanted the same system. But they also found themselves pretty special, and they didn't work together at all. They had their own management, their own budget, their own product owners. And they asked the IT department pretty much at the same time, can you build us a new system that does this and this? And as the IT department, we said, well, this looks pretty much like one system. So we can build a generic system on one end of the spectrum, but we're also getting 3 different requests from 3 different independent business units. So on the other end of the spectrum, we could build them 3 systems if they want. So building 3 systems probably isn't well, time effective, right? Because they're asking pretty much for the same thing. But if we build everything generic, we're probably going to get in trouble when we are talking about priorities and backlogs, and then one system goes down because the other is getting, I don't know, is having trouble. So doing everything generic there is also not going to work. So how in the end we solve this is we had specific teams assigned to those business units, and then as an IT department we developed a couple of reusable components for those things we were sure we needed everywhere. But then we could still cater to individual changes from the different business units because, well, we're pretty sure that working together wasn't going to work too well. So let's talk about the cost of generic solutions. It may save time in the long run to solve some generic, but at which price? I'll introduce another rule of 3, and this is that building reusable components is 3 times as difficult and 3 times as costly as building single-use component. So the price you pay is coupling, and there's obvious coupling on code level. So if something needs to change, multiple places need to change, but there's also coupling on a people and a team level. For example, if you share a library in your organization that you develop yourselves, and you want to change something there, then you probably need to talk to all the people who are using this library. What if one of them doesn't want to change and the other does want it? Who does release management, product management for these things? What about you have a new version of the library that has breaking changes and you want everybody to jump to the new version at the same time? Then you also need to synchronize their plannings. So don't underestimate the price you pay for doing stuff in a generic way. It's not a costless solution. So what if you get it wrong? And then first we need to talk about abstractions. So when you're making something generic, you're usually making an abstraction. So an abstraction is kind of an abstract concept. It's something that generalizes over the problem and solution space. So you look at what different type of problems can I have, and can I generalize over there to make it into one problem that fits all those problem descriptions. And then you also make a generalized solution space. So you make one solution that fits all those problems. So you find common behavior, and an abstraction also hides implementation details. So a type of an abstraction you probably all know, database access, JPA, Hibernate, Spring Data. The problem space is I need database access. I have queries that I want to execute, and there's a database driver. And the solution space is all databases that are supported by JPA. So the nice thing is that as a developer, you don't need to worry about database implementation details anymore. You can reuse the database access stuff you have over multiple databases, nice generic solution. And also the JDBC driver itself is an example of an abstraction. You don't need to talk, I don't know, the specific TCP protocol that Oracle MySQL does, but you can just call it JDBC API. But what are the costs of all those abstractions? So every abstraction has a cost. There are no zero cost abstractions. So in JPA, for example, the cost is, so what you gain is, well, it's easy to use, but what you're paying is, it may be hard to understand and to debug. If you write the query yourself and it fails, it's in your query. If something in JPA happens, you may need to dive into Spring Data or Hibernate to figure out what's wrong. It can be hard to customize. If you write the query yourself, just type the query. In JPA, maybe more difficult. It may be less performant because of the mapping that's going on in JPA. You may not be able to use database-specific functionality that's not implemented in JPA. So I'm not against JPA. I think it's pretty good. And we're lucky that JPA is a pretty good abstraction, right? Because many of you are probably using it. So efficiency gains of going generic are typically clear, but what if we think about onboarding new people? So we've made something generic, shared it. They need to learn about the generic stuff. Readability. If I have specific code in my class, I can just read from top to bottom this code. But if it jumps to some library that is a binary dependency, and I need to ask my friend in which library the source of this binary dependency is, I need to go there and figure out which commit ID matches to the version of the binary dependency I'm using. It makes it more complex. Coupling, we've thought about this enough. So if we talk about the cost of abstractions, well, if you're writing a bad abstraction, then you're writing unnecessarily readable code. How much time this takes you depends on how bad the abstraction is, right? You're introducing unnecessary coupling. But what about maintaining bad abstractions? If they're in your code base, the cost probably is even a lot higher. They may be hard to see, they may be hard to understand, and they may be hard to extend. So when and why should you go for a generic solution? Well, let's start with the most fun part, which are the bad reasons. We've always done it like this. Okay, and if we keep doing this, we keep ending up in the same problems where we're ending up, all right? So that's not necessarily a good reason. This one I like. We don't want to depend on libraries. Sure, so all those people in the open source community working on perfecting this library for years are delivering something that's less good than what your 3 developers in your company can do. Yeah, but security, yeah, same point. Probably if you use Spring, then there's a team working on security in Spring. We need to be future-proof. Yeah, so can we predict the future? No, etc. Because the product owner wants a generic solution. Well, the product owner can design generic functionality, but then it's up to the team whether we build something generic or not. And here is often also a challenge and I think a role for you in a team to push back. So if a product owner comes to you and says, can we build this generic so we can reuse this functionality within these 3 departments or within these 3 teams? Well, apply the 5 whys. Why? And then typically the reason is, yeah, because we do this, then they get this for free and I get more budget for my backlog, right? So the product owner does not dictate how we solve something technically in a project. Or this one, because the architect wants it. Whenever this happens, I think about my friend Charlie. Charlie is flying in right now. Charlie the seagull. So I like to call this seagull architecture. So seagull architecture is when the team is down, walking on the boulevard, enjoying their French fries, discussing how to solve problems, and the architect is like a seagull flying high over them, looking down at the team down on the ground. So seagull architecture is when the architect flies down, shouts, "Ah!" and steals the fries from the developers, sits on them and goes back up again. So the problem here is that the shit is only going down. And for an architect, I think it's important to be involved in the results of the designs you make and the architecture you make, and whether this helps the team on actually delivering better software faster. So the problem with this is that there should also be a feedback loop backup. So whenever somebody does this, introduce them to Charlie the Seagull. So valid reasons to go generic. The rule of 3 checks out. It's the third time you're seeing this problem. Now you understand the problem domain. Now you can generalize. You're pretty sure you're going to need it almost everywhere. Logging, metrics, authentication, those kind of things. Don't build authentication yourself, by the way. A library that a lot of teams will use because it's, I don't know, complex functionality or something that you will use almost everywhere. And another reason that's in a bit different aspect is complex logic or skills that only a couple of people in your organization have. So if you genericize something and you put it in, let's say, a reusable library, then it's also a way of encapsulating this functionality. And you can say, okay, this library can only be touched by this team who has the capabilities to work on this functionality, and other people cannot change this. And when the gains are bigger than the cost. But the point here is that you typically see the gains in it's easy in the future, but you don't see the added cost in coupling and planning overhead, etc. So think back about those layers in hierarchical decomposition. If you think about code versus component versus service. Are the considerations of going generic and specific the same on every level? It depends, I guess, but I would say that the risk when you get it wrong is higher when the level is higher. If you make a wrong choice on an organization level, to go generic or specific, you're paying typically more than you make a wrong choice on a project level. But also don't confuse generification with standardization. You can perfectly fine standardize on doing REST in your organization, but it doesn't mean you need to build a REST client library that your whole organization uses. So to do a small intermission, and then we're going to wrap up in a minute or 8, we're going to look at a little hobby of mine, which is code challenges. So one is code golf. Has anyone of you ever played code golf? So with code golf, the goal is to solve a problem in the least amount of characters of code possible, which is awesome. So I played this at the Javelin conference a while ago, and the task was that you needed to build a verification function for, I think, a German bank account number, something like the 11 proof we have in the Netherlands. And then I jumped into this, and I was one of the first to solve the problem because I logged all the parameters, and there were only 10 bank account numbers being sent, and I could see that if the second number was odd, then I could return true, otherwise false. So, well, I optimized for the test cases there. Super specific solution, super fast, I was on top of the list. Then the guy organizing the competition found out that I cheated, and he added like 1,000 more numbers, and then my solution didn't work anymore. So back to the drawing board. There are all kinds of people who were doing it way shorter than I could with bit shifting stuff that I didn't understand. But I did end up getting a honorable mention here. I built a client-server application in less than 100 characters, and it looked kind of like this. So I wrote a real short piece of code that would call some URL I registered specifically for this goal, pass the parameter, and then open a byte stream, read 1 byte, and if the byte would say 1, then it would say true, otherwise false. And now I had all the lines I needed to build a server-side solution to fix it. So I didn't win because I cheated, but still it was fun. Another one, Advent of Code. Who of you knows about Advent of Code? Who has participated in it in the past couple of years? Oh, that's less. So Advent of Code is a programming competition where you get challenges every day of December until Christmas. So one of those challenges, and I usually compete with colleagues in this. So one of the challenges was you get a lot of text, and then you needed to process text input. What you needed to do is you needed to the concept was there's a harbor where containers are stacked up, or crates or boxes, and you need to move those boxes according to instructions. So you can see it in the bottom here, there are here like 2 crates on stack 1, 3 on stack 2, and 1 on stack 3. So here it says move 1 from 2 to 1, which means you move D from 2 to 1. And obviously this is trivial, but then the actual input will be something like this, a bit more complex stack of crates, and I don't know, a couple of hundreds of instructions. So when I saw this, my engineering mind already went, matrices. I need to build a generic matrix implementation because I may need this later, and then I have this generic matrix implementation that I may need later. So my code looks something like this. You don't need to read this code. You are reading it, aren't you? But it was like a generic matrix implementation. And then I saw my colleague's implementation, and it looked like this. You can even see that the entries are not aligned, right? Who cares? Speed is the only thing that matters here. So by the way, this, this was the code from the CTO versus the code of the CEO. Which one did you like better? The second one is simpler, right? So the pure goal is speed here. So it was also a more specific solution. I didn't end up needing any of this reusable matrix code. So this is a good example why specific is typically a lot faster for the first implementation. But you can also give a counterexample where generic can be a lot faster. Think how you handle exceptions in a Java or a Spring application. You can write an exception handler for every endpoint or every screen, or you can do something like this with Spring AOP. So this is an exception handler, which is a controller advice, so it wraps around every REST controller. And if there's an exception, it translates this in an exception message and sends it back. Super simple, super clean, and it's definitely less work than writing exception handler for every place you have in your code base. Then a final example about website code reuse. So at OpenValue, we have a couple of websites, our main site, our blog, our training website. But my favorite website is openvalue.cat. And this has a site that has all our cats listed there. So the first version we built was the simplest thing that we could do, just hard-coded HTML. And then refactored a little bit to a generated site based on a JSON definition of cats. But then, well, the dog owners got mad, since we had openvalue.cat and not openvalue.dog. So, well, we then got ready to launch openvalue.dog, which looks like this. We have less dogs. But because of the rule of three, we didn't make a generic pets website. So we just copied the code, changed it into dogs, put it live, etc. So until we make a third website to show our horses or lizards or whatever, it's going to stay like this. So we have a couple of minutes left to quickly dive into this bonus topic, sharing code on the scale of an organization. So sharing code efficiently at scale is pretty hard, because it means that there's multiple modules in your organization that share code, multiple team members that work on it, lots of change, and preferably little or no loss of productivity. So the challenges you have is how do you refactor stuff in a central library that's used everywhere? What do you do with versioning? Do you have a versioning scheme or not? Who reviews those changes? What do you do with builds and your code base? Do you put them all together in a monorepo or not? How many of you are working with a monorepository? How many of you know what a monorepository is? Oh, that's about half. So really quickly, you have one large repo for a group of projects, or possibly all your projects in your company. So the good part of this is it's super easy to make changes across projects. You have your generic libraries, you change it there, you change your code, it's in one commit, super easy. The bad thing is that usually after time, your build time becomes a lot bigger if you're building everything at the same time. You get dependencies between different modules. But then people says, yeah, but Google has a monorepository in their trillion repos it has. Yeah, Google probably also has a team of 100 people optimizing their build tools to make sure this works. Your organization probably doesn't. So some considerations in when you share code within your organization is first a process of discovery. So, well, what code or libraries do you have and where can you find them? Distribution, do you distribute them as source or do you build binaries that are versioned? How do you import the shared code? Do you have well-defined APIs or you go YOLO? How do you handle versioning? Upgrades, do you force upgrades to your consumers of your library? What do you do with lifecycle management? And who maintains those generic libraries? Often you see that they end up between teams because they're not part of the business domain of a team. So a possible approach is to apply an inner source culture. Basically, you mirror what open source does. Every project has a couple of maintainers who are responsible, and everyone who wants can suggest changes, the maintainers review it, go ahead. And those maintainers don't even need to be in the same team. It can be a group of people from different areas who turn out to like to be able to edit and support this library. So to summarize, should you go generic or specific? Well, consider YACNI, the rule of 3, the 5 Ws. Don't forget the second. Think about the cost of generic solutions. Think on the scope of level. On the organization level, the impact is usually higher. And think about Conway's law and impact it may have in working together in your organization. So now the answer to this question is super simple. Should we go generic or solution? Well, should we go generic or specific? It should be based on a careful analysis of the problem or scenario. So the only honest answer is, it depends. But I do hope you have a couple of practical pointers. So in the end, it's not necessarily about getting it right from the start, but getting it right from the end. So someone once said that a program that works perfectly but impossible to change will become useless. Whereas a program that does not work but is easy to change, it will become and remain useful continuously. So if I need to give you one piece of advice that I hope will stick is write simple code. That's it. Please go kick some ass with your newfound knowledge. We don't have time for questions, but I do hope that if you like the session, you rate it in the DevOps app. Be honest, but also be generous. Thank you, and enjoy the rest of the day.
All systems are nominal. Initialize Genesis sequence.